everyone for this morning session. So we have a great pleasure to have Yi-Zhi Huang from Rutgers University. We talk about representation theory of UI.
Okay, thank you very much. Thank you for inviting me. So for this conference, I've actually come here to learn. Because later at the end of the talk, I may want to ask some question, but see, I already talked to Colin and Remy, so I do believe that Liouville theory, the construction of Liouville theory, will help the representation theory of vertex of it. So my talk is because this our method, certainly we do need to use analysis, but mainly complex analysis, and also a lot of work are using algebra. So I do not really want to get into technical thing. In this talk, what I want to talk about is mainly give a review of those results to construct two-dimensional conformal field theories using the representation theory of vertex of algebra. And then I want to discuss what kind of problems we cannot solve, and hopefully Liouville theory will provide us some solution. Okay, so this is what I would like to talk. So first of all, just to mention that the two-dimensional conformal field on the plane was first formulated by Radov, Polyakov, and Lodikov. I think that before their work, there are already some work on conformal field theory, mainly in string theory. So the classical vertex operator actually arise before that work, but it's not systematic. And so it's important that the BPZ formulation, they are actually using the method of a conformal bootstrap. So basically they have the formulation used for full conformal field theory, and also for conformal field, the chiral conformal field. So for full conformal fields, it is single valued because the quantum field theory, the two-dimensional conformal field is supposed to be single valued, but the nice thing about conformal field theory compared to other theory is that you can factorize into holomorphic and anti-holomorphic parts. But when you factorize, you will have multi-valueness. So you will have the multi-valued functions. So the vertex operator approach, I should mention that our approach is completely opposite to the Liouville theory approach. Liouville theory approach is, basically there are actually the two, I think in physics, basically there are three approaches to quantum field theory. The first is so-called the algebraic quantum field theory method using von Neumann algebras and so on. These days, it is also very successful using the conformal nets to construct a modular tensor category. Then the second approach in physics is this approach of operator approximation, and this corresponds to the vertex operator approach. And then the third approach is the path integral approach. This is exactly the Liouville theory approach, and so it is the probability approach. So our approach is completely different from the probability approaches that we actually start with. First of all, start with the chiral theory. So we see the probability approach. You start with the full conformal field theory, both chiral and anti-chiral. We always start with the chiral theory, and for chiral theory, we start with the simplest on a sphere. On 3 points, but this is still too complicated because in general it's multi-valued. So what we do is that we first discuss single-valued the fields. So these actually corresponds to vertex operator. So we actually first consider. So this is certainly the motivation. It's not a definition. If we have a conformal field theory, we'll consider meromorphic fields, and then the BPZ. They write out this operator approximation, so you can talk about this operator approximation of these meromorphic fields. They actually form some kind of a algebra. And this algebra in physics, they call this chiral algebra. This is equivalent to the vertex algebra. And mathematically, the precise notion of vertex algebra was introduced first by Borchardt and then also by Franco Lopez-Merman. They actually put some additional information, including the Virasoro algebra and so on. So roughly speaking, vertex algebra are algebras of meromorphic fields in two-dimensional chiral conformal field theory. So here's a precise definition. Actually, I do not give all the axioms. I just give the main axioms. The first thing we need is that certainly we need a space, but because we only consider meromorphic type of fields, so it is a graded space graded by integers. So the grading is graded by the eigenvalue of L0. Okay. So in the case of meromorphic fields, you only have an integer grade, integer weight. And certainly we need a vacuum. As a vertex of we need a vacuum. And we also need a conformal vector. Conformal vector corresponds to, see, in quantum field, we have a state field correspondence. So the field corresponding to this omega is actually give us the stress energy tensor. So that's certainly something we need. But the main ingredient is a vertex operator map, which actually maps it can be understood as a kind of operation, multiplication. It's you have a v tensor v, two elements, and then multiply together to get another element. But the difference is that it will depend on a variable x. And this double parenthesis means Laurent series, which has only finitely many negative powers. Okay, and then certainly they should satisfy some axioms. So I will not list all the axioms. Other axioms are relatively simple, but the two axioms are important. One is the so-called L-1 derivative property. When you take the derivative, it corresponds to the element inside. You actually apply the L-1. L-1 is one of the Virasoro operator because for this y omega, this actually generates all the Virasoro operators. So this is the L-1. And the most important axiom, okay, I should say that this most important axiom, there are different way of formulating. If you read vertex operator book, mostly it's not formulated in this way. But see, for me, for the things I want to talk about, this formulation is more relevant. So I will just use this. So the main thing that this corresponds to the operator participation and also the so-called locality in the bootstrap. So here the main thing that you can multiply two conformal fields, meromorphic fields, and you can multiply in the opposite order. And then you can also so-called iterate, you insert this inside. These three series, they should all be convergent in the corresponding region. The regions are different. So this is in this region, the second one is in this region, and this is in this region. But they all converge into the same rational function. So that's why meromorphic. Meromorphic means that it must be meromorphic functions. So in this case, it's a rational function, and the only pole are at these points. Okay. So the main thing is that we have these two as the main axiom. There are other axioms, but it's minor. Okay, so this is
which series converge?
Yeah, these series should be convergent because these are Laurent series. These Laurent series, the axiom says that these series should be convergent.
So each YV is a Laurent series.
Each of this is a Laurent series. This is a Laurent series, this is another Laurent series, but in different variables. So we multiply some two variable Laurent series, and the axiom require that they converge. So the nice thing about vertex operator that's meromorphic is that there are many methods to construct such vertex operator using purely algebraic method. Okay, so this is, make it easier to obtain a lot of examples. Like some example like the W algebra and so on, it is more difficult to use other method, but using the algebraic method is easier. Okay, one of the things for today's talk I want to specifically mention is that at least in our approach, okay, the whole construction works. We always need some finiteness condition. Okay, so this is exactly something that I want to learn the probability approach, because there are some cases that we do not have a finiteness condition. It seems that the probability approach still works. So, but in our case, we always need a finiteness condition. So the one of the finiteness condition is this so-called C2 cofinite. C2 cofinite is that we actually have consider subspace of the vertex operator algebra. You just apply this vertex operator on the vector, and then this is the Lorentz series. You take this is actually the coefficient of x to the first power. Okay, if this space almost span the whole algebra, then this is called a C2 cofinite. Okay, that's the very important condition. So the most relevant example related to this Liouville theory is actually this Virasoro vertex algebra. So the main thing that we consider Virasoro algebra, and then see we have this triangle decomposition, and then the main thing that we actually consider these subalgebra, and on this on the complex number we have action of the positive part act on this as 0. 0 part has two parts. One part is L0. L0 acts on this as 0, and also the central charge part. Central charge part acts as a number. So this is make this one-dimensional space become a module for this subalgebra. And then there is this standard in algebra. The standard the so-called induced module construction. You have an action of this subalgebra on this, and then the universal algebra tensor over this. Okay, I should put the universal algebra around this. Okay, and then this construction gave us a module for the Virasoro algebra, and using the so-called the PBW theorem, this linearly is equivalent to the universal algebra of the negative part. And then we actually have to do one more thing to get vertex of algebra. We wanted to actually make the L0, L minus 1 acting on the number 1, it should be equal to 0, because L minus 1 acting on vacuum must be 0. So you actually take a further quotient. And then after you take this further quotient, then this has a vertex of algebra. This is the Virasoro vertex of algebra. Now the main thing that for this is the vector space of the Virasoro vertex, and then the vacuum is just the number 1. Okay, this is inside of the universal algebra of negative part, and the conformal element is just given by L minus 2, applied to 1. And certainly I didn't give the vertex operator map. This is complicated, so I would just say that one typical vertex operator. What happened to it? Okay, one typical vertex operator is given by the stress energy tensor. Okay.
Should I think of the 0 in V of C0 as a conformal weight?
Yeah, that's basically here we actually assume that L0 acting on this as 0, so that's the 0. Okay. So this is we actually have a vertex operator, and I should mention that actually in conformal field theory, when we study modules for Virasoro algebra, we never study general module for Virasoro algebra. So this is not a representation theory of Virasoro algebra. Actually, the module we study for Virasoro algebra are always modules for this vertex operator. Okay, so that's the reason why the Virasoro vertex operator is the relevant one here. because you never study those Virasoro algebra module which has conformal weights goes to negative infinity or something, right? Okay. So now let me just outline the approach of the representation theory of a vertex of algebra. Our approach is that, should first mention that representation theory of vertex is one of the most successful approaches. Right now, there are three most successful approaches. One is the conformal nets approach. The other is the probability approach, and then we also have the vertex of algebra. So in this approach, what we do is that we first construct the chiral conformal field theory. So and then certainly the corresponding you also get the anti-chiral one, and then put chiral and anti-chiral together to obtain the full conformal field theory. And then the how to construct the chiral conformal field theory. See, the vertex of algebra is not, in general, is not a conformal field. Okay, so in the genus 0, you can say that a vertex of itself is a conformal field theory. So just like in your talk, indeed, for genus 0, it is fine. But see, if you go to genus 1, you do not have model invariance. So what we have to do is that you actually have to look at modules. Okay, you have to construct modules. These modules, if you take all the modules for the relevant vertex operator, then these are the status space of the chiral theory. And then you have to introduce these endpoint correlation functions or endpoint conformal blocks. But the main thing that you have to prove these basic assumptions for chiral conformal bootstrap. So that the chiral conformal bootstrap, there are certainly a number of axioms. The conformal bootstrap method is basically an axiomatic method. You assume these basic axioms and then derive consequence. Okay, but in our approach, the main difficulty is to prove that these assumptions or axioms in the conformal bootstrap actually is true. And then certainly there are more because Segal actually has this formulation of conformal field theory. So I think that if you look at some of the Segal's paper, he only have a definition for the full conformal field theory. But some other paper he do actually introduce very important so-called model functors and weakly conformal field theory. So these are for chiral. So we also need to verify Segal's axiom. And the main thing that at this moment everything works, mainly that we need some confiniteness condition on the vertex of algebras and modules. Okay, so this is one of the conditions is the C2 confiniteness, but for some of the property we can also have a weaker condition that the C1 confiniteness I will later discuss. So this is the strategy. Okay, so let me just briefly mention what are modules. So modules, the difference between modules and algebra is the following: that so module is certainly a graded vector space, but this time module can be graded by not just by integers. It can be graded by, in general, it can be graded by complex numbers. And then we also need a vertex operator acting on the module. So this is basically, if it's a module, you must have an action of the algebra on the module. So that's the corresponding action. And then the axiom they satisfy is that basically the same axioms for algebra. So certainly any kind of representation should have to satisfy the same property. That's roughly speaking. Certainly only when it makes sense. So including what I mentioned, the main axiom, we have the meromorphicity, associativity, and commutativity. So it can still be formulated for modules. And for module, I want to mention that we also have some kind of finiteness condition. So we can formulate the same C2 confiniteness. The C2 confiniteness can be formulated completely. Oh, I'm sorry. Here it should be C1W. C2 is that we also have C2W, but this is you should here it should be -2, and the C1 is just you have a -1. -1 is the constant term of this. Okay, so that's another very important condition. Okay, so we need the modules, but the main object we actually want to study in the vertex of algebra theory are actually the intertwining operator. So intertwining operator is you have 3 modules, and then you need a map. But this time, okay, here we actually use this notation that this braces X means that these are series, which series in X to power, but the power does not have to be integers. Okay.
So the power of the conformal weight.
Yeah, usually it's the power of difference between the conformal weight of 3 minus and so on. Okay, so it does not have to be integer. Okay, and also in many cases it is possible in the logarithm theory, it is possible that you might have logarithm. Okay, so this is explicitly multi-valued and satisfy the same axiom we actually have before, which still makes sense. Okay, including these type of things. But this is for the vertex operator acting on modules and also this intertwining operator. So intertwining operator. So this is certainly defined in the framework of vertex operator, but they are actually the same as what usually people call 3-pointer conformal blocks on a sphere. And the main goal in our construction is that we wanted to construct all the conformal blocks, the n-pointer conformal blocks on arbitrary Riemann surface using this intertwining operator. You just want to build up all the Riemann surface using sphere with 3 points punctures, and then if you have a conformal block on the 3-point sphere, you can actually build up everything. So that's the main thing we need to study. Okay, now let me just discuss these results on the C2 cofinite vertex of algebra. So this is the strong case, so that we can obtain all the nice results. So the assuming that we have this kind of a C2 cofinite vertex of algebra, so we usually also need additional condition that the vertex object does not have negative weight states, and also the 0 weight is just there's only sort of one vacuum. Okay, and then for modules, we actually want to consider some kind of a quasi-finite dimensional modules. So quasi-finite dimensional means that we certainly have an infinite dimensional space, but these are graded. But see, whenever these weights are less than something, then this is finite dimensional. So that's the module we want to consider. And then we want to consider modules among these, the intertwining operator among these modules. So here are the results we actually obtained. Okay. First of all, on genus 0 and genus 1 conformal field theory, we actually using the representation theory of vertex of algebra, we can actually prove the commutativity and associativity of the logarithm intertwining operators. So here, commutativity and associativity, in physics, commutativity corresponds to so-called the locality. But in this case, because it's chiral, so I will explain in detail. Because it's chiral, it's not really local because of multivalueness. And associativity is nothing but the operator approximation for these intertwining operator or conformal fields. So this is proved certainly under the assumption I already stated. So these are proved using the representation theory. And then we also proved the modern invariance of these integers. So what is the modern invariance of these inter-20 operator? So the main thing that we have these inter-20 operator, you can multiply them together, assuming that these inter-20 operator apply to one module and then come out also in the same module. Then you can take a trace. Okay, so we take some kind of a Q trait. You have to modify so I will explain later. You have to modify a little bit the Q trace, and then these Q traces they form a space which is invariant under the action of the SL2Z. I will explain more detail. So you see here, I want to mention that the first steps in the proofs of this are always need to prove convergence. Okay. For example, when you take the product of two inter-20 operator, because these are formal series, so you need to prove they are convergent. And then when you take the trace, when you have an infinite dimensional space, when you take trace, you also need to prove convergence. Okay. So now let me explain in detail what these properties mean. Okay. So commutativity is that if we have these inter-20 operators, then the commutativity is that when you have start with a y1, y2, you can write out the product. Okay. And then there exists y3, y4 such that certainly you also have write down this way, and then both of these will be convergent. You have to prove convergence, and they convergent to analytic multivariate analytic function. They are analytic extensions of each other. So that is the statement of the commutativity. So here the main difference from what usually for the like a full conformal theory. A full conformal theory sort of here the y3 and the y4 can be taken to be the same as y2 and y1, but here it will be very different. Okay, but this is can be proved. And then we have the associativity. Associativity is exactly the operator per expansion. So it just says that you start with some two inter-20 operator or two conformal fields. You multiply them together. You can always the operator per expansion says that you can always expand this in the in series. It powers and logarithm of z1 minus z2. Okay, so we can prove that. So the main thing that certainly this is convergent in one region, this is convergent in another region, but in their intersection, because this time they do have an intersection. In the intersection, they are equal.
Do you mean what you wrote, or do you mean you can find a sum of y5, like you have an index?
Existence. This you can always find some y1, y5, y6, such that this is true. But see,
W7 is not assumed to be irreducible. So okay.
Yeah. The moduli are not irreducible. If you actually want these to be irreducible, and you want to choose the basis of inter-20 operator, then you see there will be a lot of coefficients. Right. That's the so-called fusing coefficients coming from these things. Okay. And so I just wanted to say that for the commutativity, for the whole theory, usually there's an interpretation called the locality, because when you switch the order of the two conformal fields, they're supposed to commute. But in this case, they never commuted because in general they never commuted because in commutativity the other y3, y4 are not the same as y1, y2. So in this sense, it's not really local, but it's understandable because we are working with the chiral theory. Chiral theory, it's multivariate. It involves which path you go and so on. So it's more complicated. And then the associativity is exactly the operator per expansion. Okay. Now let me explain the model invariance, what I mean. Okay. Model invariance is that you take a set of inter-20 operator, and then you can take the main thing that you can take the suitable. See, in the rational theory, we actually take just the trace. Okay. This is actually in Segal's formulation. But in the logarithm case, if you only take trace, it's not enough. So actually, the Segal's formulation of the weakly conformal field theory must be modified to include the pseudo trace. So here you have to take some kind of pseudo trace. Pseudo trace, it is basically you can think it this way. What is the main property for trace? The property of trace is that as a trace of a product two operator. The product two operator can just you change the order to give you the same trace. So that's the main thing you can characterize a trace. So mainly is that in the case that if we have some associative algebra which is not semi-simple, then the trace is not enough. You have to also introduce pseudo trace. So anyway, I would not want to get into technical detail.
Sorry, I actually would like to know what is a pseudo trace?
Pseudo trace is if you discuss this, it's more complicated. It's like you actually have to have a left action of some associative algebra.
Which is associative algebra?
And then take any.
No, but in this case, you have a particular pseudo trace that you're applying to a
Yeah, this pseudo trace involves some phi. So the main thing that you need some additional associative algebra. Take arbitrary associative algebra, acting on the right to this module here, and then the main thing that you want to make sure that this must be a projective module. And on projective module, there is a trace, but that's the trace is still end up in the algebra. So you have to take a linear functional on that algebra. That's the phi. Okay. And then
you think there is some associative algebra such that W until is
this pseudo trace involve an associative algebra and an additional the linear function, symmetrical linear functional on the associative algebra. And we will require that this module as a module for the associative algebra must be projective, so that for projective module there is a trace, but the trace is inside the associative algebra. It's not in the coefficient field. So you need the symmetrical linear function to actually get the number. That's yeah. Anyway, this is technical, so I do not want to get to the technical thing here. So the main thing that anyway, for rational theory, this is just a trace. Okay, and then the main thing that one has to prove that this is absolute convergence in this region, and it can be extended to a multivariate and functions on this region. Okay, so these are the region for torus and so on. Okay, so this is still not a model invariance. This is the first step. How do you prove a convergence? In our case, because we have C2 confineness, we derive differential equations. Okay, so we consider the space of all such multivariate functions. Okay, and then you can define modular transformation. Modular transformation is just because these depend on tau and z's and these elements in the modules, so you have to do the corresponding change. So this is just the modular transformation of SL to Z, and why we have this? It's because L0, if this is homogeneous, L0 acting on this is just a number. So this is basically says that this thing should be understood as a kind of a form, the differential form, so that differential form, when you do these change of variables, actually it come out of these factors. Okay. So this is the modular transformation. So the statement of modular invariance actually says that if you start with some element in this vector space, and then you apply the SL to Z modular transform. Sorry, what is that? Okay. You apply this modular transform to this, and this space. After you apply the modular transformation, it is still inside here. And therefore, this is SL2Z module. Why this is important? Because when we write down the Q trace, it corresponds to the Q trace corresponds to torus with a cut, with a particular cut. And so this is corresponding to an element in the Teichmüller space, not in the modular space. And if you want to make sure that the things is defined on modular space, you have to make sure that under the action of the SL2Z, the vector space is invariant, so therefore you get a vector space over the modular space. So that is the reason why this is important. Okay, so this is the modular invariance. Okay, yeah, so this is exactly what I explained. So this is the, because the upper half plane for the tau is actually the Teichmüller space, and then this is give us something defined on the modular space. And this is what conformal field theory is about. Okay, so the main thing that I just want to mention that what I discussed these results. These are actually the main axioms used by physicists in the conformal bootstrap method. So basically, for all the physicists' work, so say for example, so like you proved those formula, how to get to the formula, they assume these conformal bootstrap assumptions, and then plus some other guesswork, and then they can derive these formula. But see, for mathematically, we actually need to prove these basic assumptions of conformal bootstrap. So basically, in the C2 cofinite case, we actually can prove all these things. But see, unfortunately, Liouville theory is not C2 cofinite. Okay, and so modular invariance is the main assumption for genus 1 conformal bootstrap.
Just one question. Physics, they say if you have genus 0 and genus 1, it's okay, there is more cyber argument.
Yeah, the main thing that if you have genus 1 and a genus 0, the assuming, so here the main thing that for high genus, you need still prove additional convergence, just like in the genus 0. After you prove the convergence, you do not need to worry about the modular invariance because the mapping class group, the main thing you need to prove that it is invariant under the axiom mapping class group. So basically, this is what Segal said. They say that because the mapping class group for arbitrary Riemann surface can be decomposed into products of mapping class group for genus 0 surface and genus 1 surface. And genus 0 surface is just given by this associativity. Genus 1 surface is just given by modular invariance. And therefore, you always have invariance under the mappings.
So the gap is just a convergence issue.
It's the convergence, but this is the next thing I want to discuss. This is already proved in our case. So before I discuss high genus, let me just say that what kind of applications we have. So the main thing that, first of all, under these conditions, but in the case of a rational conformal field theory, so the assumption I have is for C2 cofinite vertex of algebra. But for rational conformal, you need an additional assumption is that every module is a direct sum of irreducible modules. So then the Verlinde conjecture and the Verlinde formula of fusion rules can be proved. So the Verlinde, even before Mohr-Seiberg's work, he already conjectured that there's a Verlinde conjecture, Verlinde formula. So the Verlinde formula is very nice. It calculates the so-called fusion rule using the modular transformation. And then the main thing that also in the rational conformal field theory case means that all the modules are completely reducible. The category of this kind of module has a structure of modular tensor. So this is another observation by Mohr-Seiberg. So it's really important. These days, I should say that the theory of tensor category become really a hot topic. But actually, this is really start with Mohr-Seiberg, not start with the quantum group people. Quantum group in the beginning, they just study quantum group and do not really get into the tensor category, only after more established work. Okay. And then the main thing that we're actually using all these results, we can construct Segal's modular functors and Segal's weakly conformal field theory. So the one way to see this, certainly you do not have to use this, but one way to see this is that 12 actually has a book which says that given a modular tensor category, you have a modular functors. And also you can construct 3 manifold invariants. So in this case, because we already have a modular tensor category, so we certainly get a modular functor and a 3 manifold invariants. And also, Segal has this weakly conformal field theory. So using the language, so there's an abstract algebraic language that is Segal's formulation can be reformed using so-called props. It's weakly conformal field theory is the algebra of a prop of the modular functor. So basically, that's what's going on. So we can actually prove most of the axiom, but before I do this, we have to talk about the hygienist case. So as I said, for hygienist theory, the main thing missing is convergence. So in the case of rational conformal field theory, I actually formulated this as a conjecture, and then in both the rational case and the general C2 cofinite case, this convergence has been proved. So first by Gui, he proved the rational case, and then he and the collaborator, they proved the case in the general C2 cofinite case.
So what's the difference between rational and C2 cofinite? One is in
one is that every module can be written as a general sum of irreducible module. That's what we call rational. And the general C2 cofinite, the module in general cannot be written as a direct sum of irreducibles. So you have logarithm. It's a logarithm theory.
So it's more general C2 cofinite.
Yeah, it's still C2 cofinite in our case.
The C2 cofinite is more general than rational.
Yes, that's true. See that actually there are some conjectures about C2 cofinite and the rationals. For example, the people, I think, drew original conjecture that rational that if every module is reducible, then it must be C2 cofinite. But see, no one knows how to prove this, and no one even knows whether this is true. Okay. So then the main thing that in this because we have hygienist and so on. So basically, the chiral theory is constructed. Okay. So you need to put chiral theory together to actually get the full theory. So the main thing that I think that at this moment the result is still only for the rational case. For the logarithm case, C2 logarithm, we still do not know how to do this in general. Okay. So the main thing that in the rational case we can actually construct a bilinear form on the space of intertwining operator, and then prove this to be non-degenerate. The main thing, interesting thing is that to prove this non-degenerate, I have to use a formula which I use to prove the Berliner formula. So what that means is that even if you only construct genus zero theory, when you want to put the chiral anti-chiral together, you actually need some modules, because the Berliner formula is actually about related to modules. So this is a very interesting thing. In the beginning, I always doubt that why we need this formula, but see, this seems to be a deep effect. Okay, and then so this way that we can using this bilinear form, and also the results what we have on genus 0 and genus 1 conformal field theory, we actually can construct the genus 0 and genus 1 for rational conformal field theory. And then see using the results of Gui about convergence in the hygienist convergence in the chiral case, you can put them together. You will be able to get the hygienist for conformal field theory. Okay, so this is the how we actually construct a conformal field theory, starting from a vertex operator satisfies some finiteness. But I should say that how to put the chiral anti-chiral together in the logarithm case, means that it's not rational case, but still C2 cofinite, we still do not know how to do this. Okay, this is still open problem. So even in the C2 cofinite case, there are still some open problems. We still need to solve these open problems. One problem is certainly how to put them together, but there are some other problems. One is that we actually need to prove some results on determined lines. Okay, so these determined lines are not well studied, so there's something that we actually need to study. And another problem we need to actually also solve is the following: is that in our construction, we always work with graded space. You see the definition of vertex operator and modules. But if we wanted to fully prove the Segal's axiom, Segal used Hilbert space, or at least locally convex topological, complete topological space. So actually, we need to actually complete our modules to some locally convex topological completion. So I do have 2 papers giving this completion, but in these papers I do not include the hygienist information. So you need to include hygienist information, and then the verify that for this completion, it is for this completion the Segal's axiom satisfied. So this is still need to be finished. And then this is even in the rational case. Okay, this is a rational case. In the non-rational case, even we do have a graded tensor category for this module category, but the rigidity and the modularity or non-degeneracy of the category is not proved. This is rigidity is a very important property. It's related to modular gradients and so on. Because I proved in the rational case, I proved the rigidity using Bernoulli formula. So this is a deep thing, but in this case, in the non-rational case, this is still conjecture. But I should mention that in a special case that if the vertex of algebra has a free field realization, then this has been proved by Kretzig. Okay. So at least when you have a free field realization, we do have such results. And the free field realization seems to play an important role in the construction of the Liouville theory. So,
what do you mean by this free field realization?
It's just that the vertex of algebra can be embedded into some free field vertex of algebra.
And can you recall what is rigidity?
Yeah, rigidity is roughly speaking, it's that you have a dual. You need to have. Roughly speaking, it's just the given a module, you have to have a dual. In our case, we do have a dual, but see, this dual must satisfy some property. So, for example, we should have this property: W can be mapped to V tensor. We have a tensor. So the algebra play the role of the unit object in the tensor category. So you can have such a map, and then you will actually have to tensor. There should be. So rigidity is that you have to have a dual, but you also have to have these maps. One of the map is that V can be mapped to W tensor W prime. Okay, so for vector space, this is obvious. But see, now it's an abstract tensor category. So this is the map using the map that you're supposed to have. And then using the associativity, you can write it this way. And then the existence of a dual also requires that there should be another map which map this to a unit object. So this will go to this tensor with the unit object. And then this is again is isomorphic to this. So you actually can write up if you have a dual and then you have 2 maps. One map is from V to to this tensor product. The other map is from this to this. Then you can write on this composition of the maps. Rigidity says that when you compose these, it should be equal to the identity. Okay, that's the rigidity. Okay, so that's actually the most difficult part in the proof of in the construction of the tensor pair.
And in terms of say fields, I'm lacking intuition at this level. Is there some equivalent statements in physics?
I think that, let me see, the rigidity, whether, I do not know about the statement in physics, but what's going on is the following, at least in my proof, okay? In my proof is that, in my proof of this rigidity, basically, how do you prove rigidity? It's the following, you just calculate this map, okay? Assuming that in the rational case, you only need to calculate this irreducible module. When you have a module morphism from a module to itself, if it is irreducible, it must be proportional to the identity. So you only need to prove the proportional constant is not zero. Because if it's not zero, you can divide that proportional constant to some of these maps. Okay. So when I prove this, I actually have to prove this using a formula I used to prove the Berliner formula. And that formula actually is derived from the so-called Moy-Seiberg equation. So I have to see Moy-Seiberg is they're actually assuming these axioms, all these modern inverse operator power expansion, and derive these as a Moy-Seiberg equation as a consequence. So the main thing that I have to prove Moy-Seiberg's the operator power expansion and modern inverse, then see that basically that you get Moy-Seiberg equation. And the Moy-Seiberg equation give us a formula. This formula is used to prove the Berliner formula, but equivalently prove this proportional constant is not zero. So that's probably the closest to the physics, what physicists have. Okay. Yeah. So anyway, for this, I should say that another thing which is equivalent to the rigidity. Yeah. So this is probably more relevant. The rigidity is actually equivalent to the. I said it before. When we put the chiral and the chiral together, we have to construct a bilinear form on the space of intertwined operator. But that bilinear form, it's not difficult. But the difficult part is to prove that it's not degenerate. The non-degeneracy is equivalent to this rigidity. This is another way of understanding this. Okay. Okay, so examples are just C2 cofinite minimum models. So for Verasora, only minimum model are C2 cofinite. Okay, so I will finish very quickly because I already finished most of it. And then the Vest minimum weight model, but this is only for so-called compact group case. And lattice, some W algebra, orbifold theory, and so on. For these, our results apply to these things. And then beyond this, the main thing that we also can go beyond the C2 cofinite case. So when the central charge is not equal to these are not C2 cofinite. So we have a C1 cofinite. So I already mentioned C1 cofinite. In this C1 cofinite case, we can also prove the commutative associativity for the intertwined, but we in this case we cannot prove the modern inverse. Okay, so there are a lot of results about this Verasora case. So in the case of Verasora, we consider all the C1 cofinite modules. Then see we have these, and then when the central charge equal to this, we even have all these nice properties, semi-simple, rigid, non-degenerate, and so on. Then in this case, so we have these results. So I do not have time. So for affine algebra, for alpha integer which is not rational case, you can also prove something in the C1 confined case. So the main difficulty for us is that if we have a Virasoro vertex object, we have a Verma module for the Virasoro algebra. Okay, then these things are not even C1 confined. So we can define these interturning operators, but because they are not C1 confined, we cannot do anything. So the problem is that we want to prove these interturning operator among these Verma module for Virasoro still have operator approximation and so on. Okay, so this is the problem. Okay, so because they are not C1 confined, we cannot, our method does not work. So the possible answer, so after talk to Colin and Remy, I feel confident that indeed this give us a solution. So the answer, at least for like central charge bigger than 25, and so on. So this is coming from the Liouville theory. So this is something that I want to learn. Okay, and the main thing that our method is always use differential equations. So these confinedness, these conditions used to derive differential equations. So, but we do have for interturning, we do have a differential equation, but this differential equation is an infinite dimensional space. So the main thing that I want to know that whether we can extend the probability approach to a theorem of differential equation in infinite dimensional space. Then we can prove these things using this more general